Thank you. This is Felipe Rodriguez. I'm talking from London, Ontario. I'm a researcher for IVEY International Center for Health Innovation. And with me are colleagues Dr. Claudio Martin, former chair of the ICU at London Health Science Center, and also Judy Kartlak. She's the Director of Clinical Redesign for LHSC. So thanks everyone for joining us. I will be presenting the research that we conducted together using Simulate, and it is called the Discrete Event Simulation Model for planning level 2 step-down beds using NEMS. So this research is counting with myself, Dr. Greg Zerich and Dr. Dave Stanford, and also Julie, Fran Priestap, and Dr. Claudio Martin. We're from IVEY Business School at Western University, and also the Statistics Department and LHSC. So just quick comments here. IVEY International Center for Health Innovation is one of the supporters of this research. So I would like to pass to Dr. Claudio Martin so he can give a quick introduction to LHSC, and then we can resume with our problems and how we approached our research. So Dr. Claudio?
Yeah, thanks, Felipe. So just to put the coming presentation a little bit of context, as you've heard, we're from the other London in Canada, in the province of Ontario. London itself is about 350,000 population. We're a tertiary quaternary referral center with a catchment area of about 1 million, and the province of Ontario has a population about 10 million. Felipe referred to NEMS, or the non-equivalent manpower score, which is a metric that you may be familiar with as a nursing workload tool looking at ICU type interventions. The province of Ontario, every ICU within the province of Ontario collects and submits that as part of a province-wide standard data set for all level 2 and level 3 ICUs. In our center, London Health Sciences Center, we have 2 major medical surgical ICUs and a cardiac unit totaling around 69 beds between those 3 units. We don't have any general level 2 units. That's the jargon we use in Ontario and other places. They may be known as step-down units or high dependency units. We have some service-specific step-down or level 2 units, and what we were interested in was looking at opportunities for improving patient flow through the hospital that I'm sure all of you experienced challenges with, to see if there was a possibility to improve patient flow and be more efficient through a redesign of our level 3 and level 2 units. And that's how we came to be involved with Felipe's project to try to model what this might look like for us in the future. So that's, I think, a little bit of context for the work that Felipe undertook with us. Thank you.
All right. So as Dr. Claudio said, so we'll be dealing with the Medical Surgical Intensive Care Unit, the MSICU, and the one particular metrics we're using, the NEM score, so 9 equivalents of nursing manpower score. So this is originated from perhaps another metric called TISS that people may be also familiar with. But the rule of thumb here is this is a 56-point scale that measures the nursing workload, and then we're going to be using that to define step-down rules for our problem. So in short, more definitions here. We have those 3 levels of care. So the last row of this table shows level 3 care 3. That's intensive care bed. So usually there's ventilation. Patient-nurse ratio is 1:1, and these are very costly beds. And patients in ICU, level 3 level of care, they're usually they have a daily NEM score measured, and they're usually between 26 and 56 points on that one particular score. Then we have what would be the step-down beds. So usually those are non-ventilated patients. The cost goes down significantly, and the NIM scores are anywhere between 11 and 25. And then you finally have the standard ward beds, level 1 care, where you have 3 or more patients per nurse, maybe 5 or so. Those are cheaper beds, and the NIM scores are the lowest. So with all that in mind, when we got together to do this research, the university hospital site was the one picked to conduct this experiment. And we had a data set regarding 2014 where we had over 17,000 patients. And out of all of those patients, inpatients into the hospital, we had roughly 42,000 internal movements of patients inside the hospital, right? And a particular thing that came to attention was the fact that off-service, meaning the misplacement of patients into wards that they aren't originally supposed to go, would range anywhere between 5 and 30%. And Canadian hospitals tend to be busier than hospitals in the US, for example. So it's quite common that you would find congestion and then and blockage downstream, specifically in the wards. So it ends up that in the MS ICU, for the one particular year, out of the 864 patients, roughly 660 patients eventually were measured with a NIM score that would enable them to step down into a level 2 ward and releasing those ICU beds. So the idea behind was, okay, so if we know that these patients may no longer need ICU care, they could step down, how do we solve this problem? And so the LHSC had the plan to add a step-down unit. And so at first, what we wanted to do is see, what is the benefit of that one particular step-down unit coming from the MS ICU in terms of patient flow, in terms of throughput. Is there a reduction in terms of length of stay and costs? Then particularly for UH, how many level 2 beds should we need, and how efficient can those beds be, right? And finally, since we have those daily measurements of NIM scoring, so would that be in fact a useful tool to estimate the moment of patient step down and therefore aiding in the estimation of the level 2 bed needs? So basically figuring out what that one particular unit should be like in terms of capacity, in terms of patient flow, that was a big challenge. Not only because of all the complexity in terms of patient care or ICU patients, but also UH has no particular history of a medicine level 2 ward. So we had to come up with different rules in order to establish what would be a level 2 patient. There's also, the hospital has a lot of seasonality in terms of patient flow, and patients come from many different diagnostics and from many different origins. So heterogeneity is a big issue here. Also, one thing that we noticed was that patients' health and death probability, they change over time. So when we look into the data, we figured that the odds of patient survival, they increase as they spend more time into the ICU, and also the way their health progresses changes over time as well. So it was quite clear from a modeling perspective that we couldn't do anything very simple over here, and that we had to incorporate the patient's health progress and death probability into our simulation. Then some other challenges that we faced was that not only we were considering step downs as you progress to the hospital, you enter the emergency department, operating room, ICU, and then eventually step down and wards and so forth. But there's a lot of bounce back of patients coming from the wards back into ICUs and operating rooms. The hospital is very congested, so that leads to off-service and an increase of costs and length of stays and so forth. So when we first met the LHSC management, we figured, maybe we could have an analytical model to deal with this, but given all these characteristics, it was quite clear that we needed a discrete event simulation model. So that's when we decided to come up with a discrete event simulation model that had, in fact, three objectives. One, the initial one would be try to maximize patient throughput while minimizing the length of stay in the ICU. And later on, we added the idea to try to minimize cost into the hospital. And basically, our decision variables would be the number of level 2 beds and the number of MSICU beds into our simulation. So as we increase or decrease the number of these two kinds of beds in their respective units, what changes in terms of throughput and patient flow and so forth. Some of the parameters that we had to consider, and there are actually quite a few of them, are the arrival rates. So we're talking about patients coming from ER, coming from the operating room and so forth, and it changes over time, days of the week, hour of the day. So that's actually quite complex. The lengths of stays into each one of the units that we simulate in the hospital, and the death rates, or the survival odds of the patients into each one of those units. We also had to take into consideration the name scoring process. So as they are taking, as names is collected daily, so we had to figure out what exactly is the threshold that we would consider for those step down and to remain into the ICU, and how that changes over time. We also had to pick a time and place in the hospital where the beds allocated into each one of the units were roughly the same, so we can consider the changes in patient flow in due order. We had to come up with a patient flow matrix to know where the patients came to and where they go to and where they came from, and finally what kind of budget we would be dealing with when we were considering the simulation, and see the baseline scenarios and so forth. So in order to do the research, we had to collect data from multiple different sources. Gladly, LHSC has a very comprehensive patient management system. So not only we had patient registry in terms of when they arrived and patient characteristics, but we also had a very precise patient transfer file where we actually knew to the level of the individual beds where the patients came to and from each one of the units into the hospital. The nursing workloads, as NAMS, is recorded at least upon arrival and once daily, and when the patient leaves the units. So we had a very comprehensive data file showing the NAMS scoring process for each one of the patients that went into the ICUs. And with all that information, we were able to do a very lengthy and precise process of distribution fittings in terms of the arrival rates of patients into the hospital, their individual lengths of stay in each one of the hospital units, and the probability of step downs. So with that, we created the patient flow matrix and the step down rules to fit into the simulation. Overall, we had 17,380 patients that we had complete records from, and out of those, we created all the parameters for the simulation. So if I could simplify the patient flow in the hospital, this is what it would look like. We have several entry points that are quite common to a lot of hospitals, so such as the emergency department, operating rooms, but also several different clinics in town. Also our sister hospital, Victoria Hospital over here, and transfers from different hospitals in the region. So when patients come into the hospital, they come exactly through these entry points, and from there they can go to any one of those 3 levels of cares, right? So the level 3, level 2, and level 1 being the wards. So when I first approached this research, I had the idea that patient flow would be quite linear and flowing downstream. What we find is that actually patients go to and from all of these places. So the transition matrix is actually very complex, and we had to address that to a very high level of detail. So currently there are 2 level 3 units, the CSRU and MSICU. We are focusing particularly in MSICU patients. The current level 2 units are very specialized for transplant and neurology and CCU care, while the different wards have their own kinds of patients. So if we can translate this one chart into a flow matrix, this is what it looks like. So from the patient transfer files, we were able to figure out exactly what are the odds of patients going to and from everywhere. So for example, since we're talking about MSICU, so this one particular intensive care unit, 8.6% of patients from that one unit are routed into operating room. 16% of those patients here in the bottom center of the chart, they eventually go into the 4th floor, and 22% of the patients, unfortunately, they end up dying. So we were able to feed in all this information to the simulation and see how the simulation would perform. So this is a sample screen of our model. So like I showed before, we have several different entry points. The emergency room here to the top left. We have Victoria Hospital here on the bottom left corner, the operating room. Here also in the bottom left corner, different ICUs, level 2s and wards, and patients can eventually die or be discharged or transferred to different hospitals. So if you allow me, I'm going to show the model running for a little while. So this is a static screenshot. Let me see if I can, hopefully this is going to work. I can show a little bit of the simulation working. So this is just a sample simulation of what we did. As you can see over here, we have patients coming from the ED and operating room, and they're being transferred to any of those units, right? So let me speed this up a little bit. We can see that the simulation is populating the hospital. In particular, let's take notice to the center part of the simulation where we see the MSICU patients as they go up and down in time. And then we have several different key performance measurements that we're tracking, such as the number of patients in the level 2 units, the number of patients into the MSICU, and so forth. So if I speed this up a little bit more, then we can see how things change over time. So I'm simulating 2 years worth of simulation over here. So we have actually quite a lot of data collected from the simulation to a very high level of detail. So you can see as things change over time, the hospital becomes busier, and you see how seasonality effects, such as the operations going on only on weekdays and so forth, how all those things interfere with the occupancy of the hospital and the different units. So one of the things, so even though we're talking about patients, MSICU patients stepping down into a level 2 unit, because of all the congestion that happens in the hospital and the off-service that we encounter, we had no alternative but to simulate the entirety of the hospital patient flow. And we can see why that was wise, as we were able to track the impact of the level 2 unit in terms of off-service as well. And so if we had just picked this one particular part of the simulation, just the ICU and the level 2 units, we wouldn't be able to capture blockage and congestion and off-service. So even though it took longer to perform the simulation, it was the wisest decision to make as we had a wealth of data that we could analyze and make decisions on. So going back into the presentation, one of the things that we noticed for the MSICU is that the death probability changes over time, as well as the probability of stepping down changes over time as well. So we had to come up with a system that would mimic what actually happens in the ICU. And the first thing that we noticed is that we had to change the paradigm a little bit. So we considered the MSICU as a queue as opposed to a service. And so what happens is once the patient arrives into the MSICU, the simulation allows us to divide that patient into two different parts, one being the physical patient in the MSICU. So they are occupying a place in the queue here in the MSICU, so that would be a bed. And the other half of the patient, as we call it, the procedural part of the patient, goes into a stochastic model of death and NIMS scoring. So that one patient waits about 24 hours, and then we sample the death probability of that one patient. If the patient survives that 24 hours, the patient is then taken into the NIMS measurement. And for instance, if that one particular measurement is enough for the patient to step down, then the procedural patient is joined and then leaves the ICU. But if the patient is sampled with a NIMS score that says, oh, this is a level 3 patient, so it has to remain into the ICU, then the patient returns into the death process, waits another 24 hours, and then is sampled a death probability again. So in this one particular example, the patient might actually be sampled to die, and then unfortunately, that one patient, the physical patient and the procedural patient are joined again and collected, and they are taken out of the simulation as a deceased patient. So doing the stochastic modeling enabled us to see exactly how the length of stay of the patient is not deterministic. It is actually a function of the death and NIMS scoring that happens over time. So basically what we're saying is the length of stay is a function of how the health of that one patient progresses over time, right? So that enabled us to do many different scenarios. The first one being the ideal world where we have unlimited money and real estate, so we can add new capacity from anywhere from 2 to 20 beds into a new level 3 unit while keeping the existing MSICU beds as they are. The second scenario would be a reallocation of existing capacity. So there are currently 25 beds in MSICU. So let's see if we allocate some of those beds, we convert some of those beds into level 2 beds and see how that reallocation performs in the hospital. And the other one, the third scenario, is when we have we add 5 extra beds. So from 25 we go to 30 beds, and we allocate them between the MSICU and the new level 2 unit. So now let's go into some model validation. So we performed the simulation first with the baseline scenario just to make sure that the simulation was realistic with time and what we saw in real life. So for any comparison matters, throughput was roughly the same. Length of stay was actually very accurate. Also, the cost was very accurate. And the eventual MSICU length of stay was actually quite close to what you find in the empirical data, a little bit higher, albeit with a smaller standard deviation. So the simulation couldn't quite make into the long tail that you find in lengths of stay of ICU patients, but it was roughly, statistically, this was close enough that we could take this on, and every single other validation measurement that we found showed that the baseline model worked fine, so we could then go into different scenarios. So the first one that I'd like to show is the impact in terms of off-service. So the baseline scenario, we had the existing level 3 units and level 2 units. They had roughly an impact of 600 patients in terms of off-service. This could be patients that could eventually go into wards that they aren't supposed to go to, but they had to due to congestion. As you can see from different scenarios, scenario 1, new capacity, scenario 2, the reallocation, and scenario 3, the added extra beds with the reallocation, you can see that off-service decreases a great deal once you add the level 2 unit. Then we could also see in terms of throughput what happens in the hospital with both the MSICU and the level 2 unit. So this chart shows in the x-axis the number of level 2 beds that we are adding to the scenarios, and the y-axis is the number of patients, throughput of patients per year. So if you follow the blue lines, this is MSICU throughput. Scenario 1 stabilizes roughly after 8 beds or so, while scenario 2, when we are reallocating beds, there is an increase in throughput, and then you see this concave behavior as the number of level 2 beds decrease, MSICU beds decrease, then patient flow is constrained and throughput drops quite sharply. When we add beds into the third scenario, then you can see we have a broad range of scenarios in terms of level 2 beds where throughput is roughly the same. So anywhere between 8 and maybe 16, 18 beds in terms of level 2 beds would suffice in terms of throughput. And you can see a similar behavior happening in terms of level 2 beds. So first scenario stabilizes roughly after 8 or 10 beds. The second scenario, there is a concavity where you find around 12 beds. And third scenario, you have a broader range in terms of throughput. Utilization rates, again, you want to have empty beds in case of surge of patients, but you don't want to have too many empty beds. So in this one chart, again, we show in the x-axis the number of level 2 beds into the simulation and the utilization rate on the y-axis. And you can see the blue lines. First scenario, utilization rates drop dramatically, and they keep on up until a 30% utilization rate. That meaning there are many empty beds in the end. The second scenario, you see the convexity that we saw earlier, roughly around 10 beds where you reach the minimum utilization. And then for the third scenario, second scenario, you see around 8 or 10 beds. That's the minimum utilization rate you can get. So by adding those beds, you see that there's great gain in terms of empty beds and capacity to accommodate surge of patients throughout the year. This one chart shows the number of empty beds in the y-axis. So basically, instead of talking in terms of utilization rates, we're talking about absolute numbers of empty beds. So you can see that up to a point where when you add all those beds into the hospital, you eventually reach up to 17 or so beds on average, empty beds into scenario 1. That's too many. That's unused idle capacity. You don't want to have that. You want to make sure your capacity is being well utilized, while you can reach up to 13 or 8 empty beds, while today we have almost no idle capacity at all. In terms of length of stay, that was a question that we had to address. So as you increase the number of level 2 beds in the x-axis, you see that the length of stay drops dramatically, right? So we go from the original something like 160 hours or so. As you start adding level 2 beds, in the beginning there's a sharp increase, and then as you start unconstraining the patient flow into the level 2 unit, you see there's a sharp drop, and eventually you reach the threshold of roughly 60 hours. So those 60 hours out of the 160, that means a lot of extra capacity that you add into the level 2 unit as you release those ICU beds to receive new patients from emerge or from the operating room. The scenarios where you're reallocating bed, eventually as the level 2 unit is bottlenecked by the MSICU, then the length of stay starts to increase a little bit. So an unintended finding from our research was that as you have a certain number of what we call long stay patients into the MSICU, those are patients who happen to be in ICU care for more than 21 days or roughly 500 hours. As you add level 2 beds, the stochastic process of NAM scoring eventually releases all those patients, almost all of them, into the level 2 unit, right? So while we have in the baseline scenario something like 5 or 6% of long stay patients, we see that the NAM scoring process eventually leads them to a level 2 type NAM score. So they are all stepping down as you add level 2 beds. And this happens roughly around 6 or 8 beds also for all 3 scenarios. This one particular chart is, for me, what I would call the cherry on the cake. As we added estimated costs, operational costs into the simulation, we could see, and this, from an analytical perspective, this was actually quite great because you have this nice convexity here where you can find minimum points. So for all 3 scenarios, we go from a daily cost of roughly $3,500 in the MSICU. As you add level 2 beds in the over here in the x-axis, you see that the cost per patient day drops dramatically, reaching a minimum around 12 beds for basically all the scenarios, right? So up into 12 beds, there is a significant gain in terms of economies of scale that you get from adding the level 2 unit. And from those 12 beds over, then you actually start having idle capacity of some sort, and then the patient day cost starts to increase as the MSICU is reduced in size, and eventually you end up having a cost increase that could lead back into the original $3,500 cost per patient day, right? So this gives a nice little threshold anywhere between 10, 14, maybe 16 beds in terms of level 2 beds in the end, so answering one of those questions. So another thing that we wanted to see was, okay, so this works well into our current scenario. So what if we increase patient flow? And so we tried all sorts of scenarios of patient flow increase, going from 5% all the way to 30%. And in this one, so this is an example of the first scenario where we add 12 beds into the system while keeping the same number of ICU beds. We can see that number of patients waiting for disposition in ED. We don't want those patients to wait too long for the disposition. So anywhere below 5 minutes is fine. So in the baseline and this one scenario, we are roughly at 99 and 80%. As you can see, patient increase, things start to wait. Patients start to wait too long, 2 hours, 26 hours. So we see that there is a threshold where the hospital basically starts to collapse, anywhere between 10 and 20% in terms of increase, but adding those level 2 beds helps stabilize that one particular influx of patients. Throughput, so this is the chart where we have the bed mix. So we have 30 beds available, and we're reallocating beds from MSICU into level 2 beds. You see the original scenario here in the bottom, blue and orange. We had a nice long threshold where different range of beds would suit our needs. As you can see, the patient flow increases, we lose that wiggle room, and we start converging into 16 MSICU beds and 14 level 2 beds in the end. So things start to be much more responsive, and there's a lot less room to for patient surges, right? So again, so the average length of stay up into maybe 10% increase of patients, we roughly don't see any change in terms of average length of stay in the ICU, but then we see an increase in terms of hours in patient stay. So 30% increase, that's already a big deal in terms of you're adding another 5 hours into another 1,000 or so patients, so much more higher level of occupancy, and things start to deteriorate. And finally, in terms of sensitivity analysis, when we see our total bed costs, when we account the operational costs for the MSICU in the new level 2 unit, you see in the original scenarios where we had the 30 bed capacity reallocated between those 2 units, you can see that there is a range of bed mix that are roughly around the $15 million mark. And as we increase patient flow, we lose that ability to deal with the range of patients. So if we wanted to make it like something like a dynamic setting for those 2 units, we would lose that ability as patient flow increases, and then we start converging into a different costing structure, right? Going all the way up to $20 million in terms of operational cost. So in summary, what we find is, comparing to the baseline, we have 3 different scenarios where we can find optimal points, and adding the level 2 unit seems to converge around 12 beds out of the initial 25 beds in MSICU. So scenario 1, we would have too many beds available, 37 beds, that's too many. So we can actually go into different scenarios, such as scenario 2 and scenario 3, where we are reallocating beds or adding just a little bit more beds from 25 to 30 beds in total. And we can see that there's a sharp drop in terms of average utilization rates, while we can still account for a surge in terms of patient influx. So that means we can reduce a little bit the off-service in the ICUs. We can also see that the length of stay is sharply reduced, and particularly in terms of costs, we have minimum points that are significantly lower than what you would expect from the baseline scenario. Again, these are cost estimates, so we're talking about rough numbers here, but you can see there is room enough that we can reduce in many millions of dollars the current operational cost of that structure, and this is something that only a very precise simulation and detailed simulation could provide results for. So in terms of conclusions, I would like to say, first of all, there seems to be a clear positive impact especially when we simulate the new level 2 unit into the current patient flow. We reduce occupancy, utilization rates go down, length of stay of MSICU patients go down, as well as off-service and costs. So it's clear that this could have a significant impact in terms of patient flow. Adding capacity, there's a moment where that doesn't benefit the hospital anymore, so we have to be careful not to maybe overshoot or undershoot. There's a sweet spot that we can achieve. and seems that converting MSICU beds into level 2 beds would have some benefit, particularly in case of budget constraints and so forth. So in the end, adding the NEM scoring process and the dynamic, the stochastic death probability process into the simulation proved to be very useful and very precise. So this is something that I would strongly recommend. If anyone is simulating ICUs, make sure that you have the death probabilities changing over time, and the NEM scoring process, meaning the health of the patient changing stochastically. That seems to provide very reliable results. So I would recommend ICU simulations to consider those two aspects of patient health. And some of the next steps that I'm conducting and we have started to talk about would be, perhaps adding new simulations into the sister hospital, which is Victoria Hospital, or having simulations where we have dedicated long stay beds. Maybe Dr. Claudio can talk a little bit more about that later on. And two projects that I'm conducting on the side is come up with a forecasting model for the length of stay in the MSICU using those NEMS measurements that seem to behave so well into the simulation, and also see if I can simplify this a little bit and perhaps use an analytical model that would incorporate the off-service, the NEMS measurements, and the bounce backs that we see in the patient flow, and use the simulation to validate that analytical model. So this is what I would have to say. Maybe Dr. Claudio and Judy would like to add a little bit about their experience with using the simulation. So that's it.
Felipe, thank you so much for that very, very comprehensive and fascinating explanation about the simulation. I don't know if colleagues from London Health Science Centre are willing to say anything or wanted to comment anything further on this about what's likely to happen as a result.
Yeah, it's Claudio Martin again. Yeah, so the data, we've worked a fair bit with Philippe on this model and have a fairly rich amount of data to feed into the model, which you could maybe describe. We are moving ahead, making some changes. It's an ongoing project. The results from the simulation are just one tool and one piece of data that are being used by the team to consider how to redesign our whole overall bed model within the hospital. There's other constraints, physical plant and so on, that need to be considered, but the results from simulation were definitely very helpful and consistent with our conclusions from some other thought processes as well. So it's been a very useful project to be involved with on a very practical point.
Thank you very much. It's really good to hear that it's having an impact. And there's a couple of questions that have been posted. If you're okay to answer those. I'll read the first one. This is from an RN who's completing a PhD in simulation and modelling at the University of Saskatchewan, saying fascinating research and excellent presentation, thank you. Do you plan on running scenarios where you change the staffing mix? So either looking at RN versus LPN versus care aides, or changing the percentage, looking at financial impact. Can you say anything about that?
So this one particular model, the focus was in terms of how many beds we should have, right? And keeping in mind that patient-nurse ratio is an important aspect of both the patient flow and cost. So the idea was to figure out the number of beds. Now, adding staffing into the model should be another layer into the model that we could certainly do. I think as we simulated the entirety of the hospital, one could have perhaps a very bold approach and, let's have staffing all over the hospital and see how the hospital behaves in terms of nurses and so forth. Or one could just go into the MSICU and the level 2 units and add nurses there or different kinds of health professionals and see their occupancy and their idle time and so forth. So that could actually, we didn't intend to do that at first, but it can be done for sure into this one simulation, yeah.
It's Judy Kochlak from LHSC. I think it's fair to say that the skill mix initiative, again, is a current corporate initiative that is underway right now. And right now, based on the acuity measures and those patients that are admitted and occupying the level 3 beds, not so much the level 2 beds, but the level 3 beds, right now the information would suggest that we do not have capacity in terms of moving in an RN, RPN skill mix, but again, that's a corporate-wide initiative, and there are new tools that we're using in terms of assessing the acuity indexes of patients occupying beds in level 2, level 3, and the ward. But the primary function and focus right now is focusing on skill mix in the level 2 and on the ward.
Okay, thank you very much for that. A couple of other questions that have come in. So based on your simulation, what was the time span of the data you estimated?
So we had data worth of about a year of patients, and that was the minimum that we needed because there's so much seasonality involved, right? And not only it had to be a year, but also had to be a year where we had a fixed number of beds into the units, so the data would be precise to what we were trying to simulate. So, and when we simulate this, then again, we run the simulation for a couple of years of warm-up time, and then we collect data for another year, right? And we do that hundreds and hundreds of times. So there's thousands of hours of simulation into our results. But I would, because of seasonality, I would recommend at least a year's worth of data and a very long warm-up time, because the patient flow is so complex that you gotta allow for the hospital to be fully populated. And I found that 1 year wasn't enough. 2 years was good to stabilize the simulation, and then collecting data for another year, multiple times.
Okay. That's really interesting. Did you include some factors like the aging of the population?
No. So there is a host of characteristics that we could have included into the simulation, but when we were looking into the hazard rates for the MSICU patients in terms of their odds of of survival over time as they change, we were able to find a good enough fit, log normal distribution, taking into consideration time, and so that was sufficient for the simulation to run it into realistic levels. But not only patient age, but also diagnostics and so forth. All of these things play a role into the patient's probability of death and probability to step down. So, you could dig deep into those kinds of issues. But we found that, just accounting for time into that one particular population group, that was enough of a fit to run the stochastic simulation that way.
So thank you so much to everybody. Look forward to talking to you again at a future webinar, and particular thanks to Felipe and colleagues from London Health Science Centre.
Thanks so much. Pleasure to be here.
Thank you. Bye.
Bye.